and then I'll talk about the assignment. Okay, so scatter plots. Just describe what a scatter plot is. So you have a XY axis, which is your normal thing you think about in algebra. On the horizontal axis, we have some variable x, and x is what we would call the independent variable. Independent. So that's usually something we may have control over, or we think affects changing the independent variable will affect some other property, some other variable. So we have the y-axis, which the y-axis, the y value is the dependent variable. Now in scatter plots, it doesn't mean that we purposely change x. It just means that x may take on different values, and then we measure the y value and we plot them on a graph and see if we see any relationship between the two. You know, normally in algebra we draw straight lines and every point fits perfectly on a straight line. What we do in scatter plots and regression analysis is we take real data and see if, usually most of the time, is if we can fit a line to that data that best represents what the data is telling us. So let me think of something that, you know, an example of. Let's let x is hours spent studying, and y is final course average. So we take say we take Math 152, and somehow we track your, how we do that, I'm not sure, but if you were honest and you did a survey and figured out how many hours you spend studying, and then you could take your final average and we could plot those data points. So the number of independent variables is going to probably be as different as the number of people in the class. You're not going to have exactly the same hours. You might, but most of the time it'll be different. My headphones are beeping, which is annoying because I didn't bring my charging cable over, which means I got to run to my office. So let me just run to my office here. Sorry. Okay. Yes. Part of the way. I didn't run all the way. I was like, I gotta stop here. Okay. So you plot that data and you get, some kind of result like that. So you have so many pairs of x and y values. And in general, what we would see is you just say, well, it looks like in general that the more hours you study, the better grade you get in the class. That wasn't a big surprise, hopefully. And you could eyeball a curve, a straight line, and then you could come up with the equation for the line. And, let's say it's, we'll say y, y equals 1.5 x plus 10. Okay, so if you didn't study at all, you might still get a 10. Actually, in this class, you'd still get a 30 because usually that's the way I curve the thing. But you could make some judgment on, well, if I studied 3 more hours a week or 3 more hours for the class, I could get a 1 point higher, and that would give me a higher grade. Yeah, what's that? Yeah, that's why it doesn't have a perfect curve, because there are other factors that affect your final course average besides the number of hours studying. One is maybe it's a multiple choice test and you get lucky. Maybe it's just you're super smart, or maybe um, you're just more efficient at studying. There are a lot of factors besides just hours. That's why you end up with this, what we would call scatter. So the question is, how do we create a graph like this? How do we come up with the equation for the line? And we'll just open up Google here and just look at a couple of scatter plots that they have online and just talk about them. Give you some examples of what you might use a scatter plot for. So we'll go to images, scatter plot. Let's see what this one is. So this is something to do with eruption times. Oh, these are just examples of scatter plots. Okay. I was trying to see what that was. Oh, right click it. Well, then what? Just open it. View image. Oh, there we go. So we have eruption times in minutes versus waiting time between eruptions. Yeah, so in this case, you would think the longer that it would be between eruptions, the more chance that the energy would build up, so that when you have a subsequent eruption, that it's a bigger eruption. Okay, that's the general idea. It's kind of interesting that you've got sort of two areas. There's a long eruption and there's a short eruption, but the intermediates are not there that much. So that's kind of one interesting one. Let's look. What are the stuff we got here? Scatter plots. So as I was saying, this person's not. It's not like you can change the eruption duration. You have no control over it. We're not purposely controlling the. So this is a scatter plot. They're using blue people to represent males and pink ones to represent females. And so you're just looking at height versus weight in general. And we know that has some effect. Taller people are going to be heavier because, if you just think about people having the same density, if you want to call it, that as you grow taller, you're also going to grow this way anyway, not because you're fat, but just because probably the relationship between height and width and depth are probably fairly common between different height peoples, right? But again, that's not the only factor. Height is not the only factor that affects weight, but it is one of them. So again, that's an example. Here's I don't know what that one. Dispensable income versus usage frequency. I don't know what they're using. This one would be a case where you don't see any clear relationship between the variables. We would call that a shotgun plot. So it's like you shoot a shotgun and you just get them equally distributed, but it's not any kind of order to them. Now this one you get, there might be a slight trend in this direction. What is this? Income versus age. Okay, you'd expect older people maybe would make more than younger people because they hopefully would get paid for their experience. Okay, so anyway, those are just some examples of scatter plots. So what I'm going to do is show you how to do it in Google Sheets. So let's go to Dabney. And what I'll do is I'll send you a file with the data, so you won't have to input the data. There is a subsequent problem that you will have to just enter the data manually. Okay, so there's our spreadsheet. So we just need to bring some data in. So I have some data to look at. So we're going to import. I think I already have it, but I'll get it from my computer. Chapter 12, scatter plot demo. I think that's the one I want to get. Okay, and it's already in an Excel format, so it doesn't give you as many choices. So I'm just going to say replace the spreadsheet. So any scatter plot, oh no, that actually does more than the data. So let me just, the one I'll send you will just have data. I'm going to start from the beginning here. So I'm going to create a new file. Yeah, I'll zoom out in a second here. Let me get my data in. Okay, so you'll read in the data. The video shows you how to do that. And there we go. So we have X and Y data. So to create a scatter plot, you can highlight the two columns that have all the data. In this case, there are about 25 data points. And you do an insert, chart, and because I have both X and Y data, it automatically assumes I want a line plot, which I do not want a line plot. So I'm going to change the chart type to scatter plot, and actually you can see it right here. So it suggests, it's giving us a couple of suggestions, which is a line chart or a scatter plot. So we'll do a scatter plot. So let's just close it we'll come back and make some more further changes. So you can see the X versus Y data. So in general, you look at that and you'd say, if I increase X, I increase Y. There's a positive slope. If I were to draw a line along there, I'd probably just eyeball it to go through here. Now it turns out that you can have it fit a line to the data. So let's go to edit the chart, and under, oh yeah, so you go to customize, and if you go to series, you'll see right down here is trend line. It's the same thing in Excel. They don't call it a regression line, they call it a trend line. And you can see that it automatically fits a trend line, which is pretty close to what you would probably have guessed anyway. They don't give you the equation for the trend line as far as I know. Oh, actually you can show R squared, which we'll talk about. Let's see if there's anything else. Maybe it does let you do that. It doesn't look like it. Okay, so you can show R squared, which it says it's 0.764. I'll explain what that is in a minute. Okay, close it down. And if you wanted to label the axis with what the X variable stands for and what the Y variable stands for in a real trial, real experiment, you could do that. You could change the title if you wanted to. But the key thing is, all you need to do is put in the X and Y values, and all we're doing there is, it's like when back in the old days when you had a piece of graph paper, you draw the axes on the paper, you take the coordinates, the X coordinate, and then you go to the Y coordinate, put a little dot, then you go to the next pair and you put another dot, and you get a series of dots. And now this line that I have, where does that come from? Well, if you, it actually comes, the equation, the procedure that allows you to come up with the equation for that line is derived using calculus. And it's trying to minimize the distances from this line to the point as an aggregate. So if I were to slightly change the the position of this line and calculate the distances, the positive distances from here to the line, and add those up. This is in generally speaking, you'd find a larger value. So it's just trying to make it, essentially what it does is it fits the line such that the error of the data points from that line are a minimum. And it's not that, it's laborious, but it's not a complicated calculation. Now in Excel, what it'll do is it'll automatically generate the equation for you. In Google Sheets, you have to do one more step. So I'll show you how that works. So move this up to the top. So it's one of the add-on functions. So we've hopefully done some of that already. So you go to Start, XOMiner Toolpak, and you go to regression, not regression, linear regression. So the inputs into linear regression are the range of y variables. So the y variables are here. So I'm just going to highlight those data points. Instead of doing them manually, I'm going to highlight the range, put it in there, which is B2 through B26. Then I'm going to highlight the x values, and I'm going to click in there, which is A2 through A26. Then I'm going to put my cursor right over here to the right of the graph. I'm going to click in Output Range. That's cell I1. I'm not going to do the confidence level. It's already done a fit, so I don't need to do that. Really, I don't need to pick anything. It'll still give me some information, even without all this extra stuff. And I say OK. That's it. So you get this result. And that's interesting, because the r squared I got here doesn't equal the r squared I got there. I don't know why that is. I didn't change any of the dots, no. Yeah, I don't think so. That's interesting. I hadn't noticed that before. Anyway, the reason is because I've never shown the equation on the chart before. I've always just used this. So, I mean, this is 0.88 versus 0.92. They're not exactly the same. Okay, so that's important, r squared. And the other thing, if you go down here, there's a lot of stuff I don't even know what it means. These two coefficients give you the equation for the line. So we have a y-intercept of negative 2.18. So I'm going to write that out. So the equation for the line is minus, I've already forgotten what it was, 2.18. That's the y-intercept. And the slope is 0.833. 0.833. So that's the equation for the regression, for the trend line or the regression line. So it helps you predict. It gives you an idea of how much a change in x variable results in a change in y variable, given on average. And I say on average because you can see how this thing jumps all over the place. But all these things could be due to the random nature of the measurement. It could be due to that there are other factors besides the x variable that are affecting the y variable. So we call this the trend line equation for the trend line. We call it that. We could call it the regression line equation. It's the linear equation that best predicts the relationship between x and y. Now there's this thing called r squared. This is called the correlation coefficient. And how this number relates to how well the line predicts the actual data. It says so if R is close to 1, the equation predicts the experiment well. Typically you have less scatter in the data. So if I compared, say I have data that has the same regression line, if you had data that looked like this, which would give you the same regression line, but they're much closer to the line, the red dots would have a much higher correlation coefficient than the black lines. So the magnitude of the R squared is indicative of how well the line fits the data. If it's close to 0, if R is close to 0, there is no correlation. That would be like our shotgun curve. So let me just show you a curve that has a low correlation coefficient. It would be something like, so even though you could get a line that fits that data, you could run the analysis and then the line might look like that. And so this kind of relationship, R would be approximately equal to 0. There is no relationship between the independent variable and the dependent variable. The third case is if you have a negative correlation coefficient. So let's say we have something that looks like this, but the dots are like this. So if I were to fit a line to the data, there's little difference between the predicted value and the actual value. But because the line has a negative slope, so we'd say here it's approximately equal to -1. So positive slope means there's a positive relationship between x and y. Increased x means increased y. A negative correlation coefficient near -1 means that there's a good relationship between x and y, but when you have an increased y, you have increased x, you get decreased y. And if you have a correlation coefficient close to 0, then there's no relationship between the independent variable. So if you were a scientist, you probably wouldn't usually present data like this because there's no relationship. You'd be looking for some kind of relationship. So here's one. Let me. Unless
your experiment is explicitly whether something does not.
What's that?
Unless your experiment is explicitly that something
does not happen. Yeah. So if you did, well, there's two ways of doing this, the same phenomenon. So let me just show you here. This is temperature, average temperature. This is years. And then you could have CO2 level versus temperature. So if you're looking at global warming, you would see, the pre-industrial age, the numbers pretty much flat, and then you get to the industrial age and it starts to go up like this, and then it goes okay, something like that. Or it probably doesn't go that fast. The carbon dioxide level goes up that fast. Probably the temperature would be something more like this. But if you were to plot temperature versus carbon dioxide level, and make sure I get it the right direction here, you might get something that looks like that. What would probably happen is, this would be a long period of time, so you might have a lot of data points down here that correspond to this part of the time cycle, and then you'd have fewer points as this thing starts to take off. Now, it wouldn't necessarily be, you might fit it to something other than a linear relationship, rather than, this might be more like an exponential relationship. And you can also get correlation coefficients, not just for linear equations, but for non-linear equations. So let me just show you. I'm going to open up an Excel file that does the same thing as we're doing here, but looks at a few other scatter plot demo. There we go. So what I did is I came up with this way of randomly generating data, and there's a relationship between x and y. You can actually see the equation here. It's 2 plus 0.8 times the x value. But then I add this random component to it. So that's kind of adding stuff that's either random or it's not related to the x variable. So other stuff that may affect y besides the x variable, or just random nature of the process. And you can see on the Excel spreadsheet they have the equation and the correlation coefficient. What I'm trying to do is make this bigger. I think I gotta actually go in and make the font bigger, so let me do that so you can see better. Oh, didn't like that. Let's try it again. Okay, keep trying to make this thing bigger. Then it goes smaller again. Why is that? That's weird. Oh well, you'll just have to see it. So there's your regression equation. There's your r squared, 0.8471. And every time I put, that's not good. Why did it do that? Okay. There's some, I think there's some connection. I know what it is. It's because the F9 key on Excel is also, there's also an F9 key for the recording thing. So apparently when I push F9, it stops the recording. So that's why I can't do that now. So because when I'm in my office, I'm not recording it, and I'm like, why is this working? Not working. Okay. Anyway, I should be able to do this. Where is it? Formulas. Yeah. So if I do the calculate now button, you can see it generates a new set of data, and each one has a different amount of spread. You can see how the correlation coefficient changes slightly, but there's still a pretty good relationship between x and y. I mean, there is scatter this direction. They don't fall super nicely on the line, but they do pretty good. Now, actually, if I go over here and I redefine my the way I come up with the random variation, if I make that 0.5, what will happen is when I copy that equation down, it'll reduce the amount of scatter on my plot, and my r squared will go up. So now you can see r squared is 0.95, and you can see how the data is much more closely aligned with the regression line. So these are just all examples of different scatter plots, how they can vary just because of random nature of how you sample. So what if I go back to 2? If I go to 2 as my that's my range on my random number generator. If I increase that, it will cause the data to spread out more. So now I've got data that has much more. It's not as tight. It's got more of a random element to it, and you can see the regression. The correlation coefficient is about 0.5. So we would say, if we ran an experiment like this, we'd say, well, there is some correlation between the x and the y variables, but as I increase this random component, this thing is going to get less. Ideally, ideally you would see something more like this, where the spread is less, and there's nothing you can do about it. It's not that you can, it's not like you'd be cheating if you tried to make it force it to. You might be able to design your experiments so your measurements are more accurate, or to reduce the spread in the data. But these are all scatter plots. Okay, let me just show you where the video is for this particular assignment, and I'll email you the assignment and the data. So if we go here, and it's under the same folder as the Chapter 12 project.
So is that like going along with?
And this will, yeah, well, this will be separate from, this is like homework. So this will be due next Wednesday. Oh, I gotta go to YouTube here. Oh, here it is. So if you go to the playlist for Chapter 12 project, I've added two new assignments. This one I'll do next time, but it's a scatter plot assignment, and it'll show you. So it's 11 minutes. So it basically goes through importing the data, creating the plot, making some edits to the plot in terms of title, how to do the linear regression, and everything we've talked about today. Okay?
So it's due the same day that
Yeah. Okay, so that's it for scatter plots. So we're going to go to, I think we started to talk about this, but I went back and I made a new presentation up, so I think this is probably better than it was the other day. I didn't get too far. So the next thing we're going to talk about is it's estimation. And the whole idea, as shown on the screen, how do I predict with a certain level of confidence that the population mean lies between two values based upon measurements of a sample of a certain size, of a sample of size n. And that's a question mark. Kind of looks like a funny face, but it's not. So the idea is that I run an experiment of a certain sample size, and then I want to say, based on that data, what limits can I set which I feel will be comfortable, will for most of the time predict where the actual population mean is, because the sample mean's an approximation. The population mean is everybody. It's all the data, so that's an exact number. Again, it's like taking polls before an election. The election is the population because everybody who votes is going to vote, okay? But you try to take a smaller sample prior to the election to predict what is going to happen as far as the election is concerned. And you see the results. They'll say the results are this plus or minus 3%, 3 percentage points. And so we're going to do the same thing with just general data. And typically you talk about something called a certain confidence, 90% confidence. And we call this range of numbers where we say the population mean is going to be some percent confidence interval. So ultimately what I want to get to is I can say that I'm 90% certain that the population mean is between two given values of the variable. Pardon me?
Population is mean.
is mean. So I might say, based on testing of n samples, I estimate with 90% certainty that the population mean, not the sample mean, but the population mean is between 74.3 and 80.2. Typically, the sample mean is halfway between these two values. So what's the procedure? So what we do is typically we take the sample mean and we subtract some number to get the lower number, and we take the sample mean and add the same number to get the upper value. Because the sample mean is our best estimate of the population. We have no idea what the population is. We can only estimate it based upon the things that we actually measure. So in all these procedures we're going to do, the sample mean is what they say is the best estimate of the population mean. But beyond that, we want to say now with a certain level of confidence that the population mean is between two numbers, which involve the sample mean minus something and the sample mean plus something. So we have to determine what that something is. And that something is going to be dependent upon the standard deviation of the samples that we test, the number of data points that we test, and how confident we want to be about this range of numbers, including the population mean. So D is a function of the sample standard deviation. This plus or minus thing is a function of the sample standard deviation, the number of samples, and my confidence level. And I'll explain what the confidence level really means later. I'm going to kind of use a general description early, and then I'll use a more specific one later. Okay. Now, in general, what happens is if you're trying to estimate the population mean and you want to get a better answer, one thing you can do is if the standard deviation, so S stands for standard deviation, if the standard deviation of the samples goes up, then this number, the plus or minus number, goes up. I'm less confident. So let me just write out what that means instead of with the letters. It says the more spread in the sample data the less confident I am about the population mean. So I take the data, if it's, it has a mean, but if it's spread out widely on either side of the mean, the sample mean, the less sure I am about where the population mean is, just because of the way that the data is spread out. Okay. The more tightly, the more concentrated the data is around the mean, the better I would feel about predicting where the population mean is. The number of data points, when the number of data points goes up, this goes down. So that makes sense. That says what that means is that the more testing I do, the better answer I get. So if you were doing a survey and you wanted to do a political survey, you would think if surveying 100 people would give you a better answer than surveying 10 people. Right? And then finally, the last one is when the percent confidence goes up, this number goes up as well. What that means is as I say, I'm 90. If I say 90% confidence, then I can have a narrower range. But if I want to be really confident that this range is including the population mean, I have to make that range wider, because that just gives me more wiggle room, gives me more chance that I'm going to get. It's like hand grenades. What's to say, horseshoes and hand grenades? If you use a hand grenade, you don't have to be that accurate. So you're spreading out. As long as you make that interval bigger, you're more likely to have the population mean be in that interval. So those are the three factors that influence how well you can predict.
Accuracy only matters with horseshoes and hand grenades?
Yeah, right. Yeah. So let's just do this. I'll explain how the problem works. Well, no, actually, first I'm going to do this is from chapter 12, section 5, and then I'll use a similar procedure for what we're talking about. So from section 5, we can answer this problem. If the population mean is 78 and the population standard deviation is 4.5, between what two values does 95% of the data occur? It's kind of like that question with the grades that we were talking about earlier for homework. So I'm going to draw a picture of what's going on here. So we draw our typical normal distribution like this, and the center of it would be 78. And what they're looking for is they want 95% of the data. What are the values where 95% of the data lies between those two? So that's this thing. And what we want to figure out is, what is this? We'll call this A, and we'll call this B. What are the two values associated with a mean of 78 and a standard deviation of 4.2? What values of A and B are such that you have 95% of the data? So what we're going to do is we're going to use the symmetry of the normal distribution. And so I know that 50% of the data is from here to here. Also, if the sum of the two little bits on the end here, this plus that, has to equal 5%. So if this is 95%, these two have to add up to 5%. So the area associated with this tail out here is half of 5%, which is 0.25, and this one is 0.25. And if you add those two together, you get 0.05. This is 0.05, then the stuff in the red has to be 0.95. So to find this corresponding z-score over here, we're going to use the area from the mean out to here. So the area that we're looking at is 0.5 minus 0.025, which is 0.475. So that's the area, and the area I'm talking about is this area. Now, with that area, I can find the z-score, so I go to my table, and I'm looking for 0.475, which is right down there. So the corresponding z-score associated with an area of 0.475 is 1.96. So to find the x values, remember what we did is we took the definition of the z-score, which was x minus x mean over the standard deviation, and if you solve for x, you get it's equal to x bar plus the standard deviation times the z-score. So b, this b value, is going to be equal to 78 plus the standard deviation, which was given in the problem as 4.2, times the z-score, which is 1.96, and the a value is 78 minus 4.2 times, well, or plus negative 1.96. So we take the negative z-score, and we get my calculator. So 78 plus 4.2 times 1.96, we get 86.2, and 78 plus 4.5 times negative 1.96 is 69.8. So what I can say is that 95% of the data is between 69.8 and 86.2. Okay. So we're going to do a similar procedure to that to back out what we consider to be the confidence interval of where the population mean is based on the sample mean. As I said earlier, the best estimate of the population mean is the sample mean. That's why the confidence interval is centered around the sample mean. And it turns out as the number of measurements increases, meaning the number of samples increases, the sample mean is a better estimate of the population mean. So not only is the sample mean the best estimate of the population mean, but the more samples you take, the better that sample mean is of the population mean. Again, it makes sense. The more samples you test, the better the average that you're getting. You can also, not only is that sample mean a better estimate of the population mean, it also allows you to look at what's called the distribution of sample means. Okay, I'm going to try to explain what that means by showing you an example here. I think we might have looked at this the other day, but we're going to look at it in a different light. If I can find my, there we go, that's what I'm looking for. Okay, so remember, we talked about, I came up with this spreadsheet, and I have the population, which consists of 1,000 numbers that are randomly distributed around 50, an average of 50, with a standard deviation of 3. And I can go in there and I can randomly pick 13. I just chose 13 because it's lucky. So I pick 13 of these 1,000 data points randomly. And those 13 samples, those 13 values create a sample. So this is one sample, 13 out of 1,000 numbers. This is another sample, another random selection of 13 numbers out of that sample. And we were saying that, I think we were saying that, it's hard to remember which class I say this to, that when you take the means, even though the numbers vary here between, a low of 46 and a high of 58, the mean values are pretty close to 50. And if I had more than 13 values, this number would be a better prediction. Also, what you'll find out is that if you do a distribution of these sample means, it turns out that the distribution is a normal distribution. So the sampling distribution is normal. And if you then take a number of different samples and you look at the distribution of the sample means, which are all these numbers, so I take these and I do a histogram of all those numbers, you find out that the histogram of the sample means, not of the sample, but of the means of the different kinds of samples, also is normal. And as you increase the number of data points in your sample, this histogram of the sample means the variation gets smaller and smaller. Okay. And what we're trying to determine is when we're looking at this, instead of a histogram or a normal distribution of looking at the sample data, we're trying to look at what we would predict the distribution to be of the means, because we're trying to prove the whole purpose here is to prove that ultimately that the difference in two numbers, two measurements or measurement versus some standard, is due to actual differences in the population and not due to just the random nature of selecting samples from a population. Because you can see that as I go through this process with the same population, each sample gives me a different number. None of them are exactly equal to 50. Some of them are above and some of them are below. So it's the whole uncertainty of the sampling process and the uncertainty associated with not having a huge amount of samples compared to the population. Okay. So this distribution here is not the distribution in the sample. What is that for? Oh, I thought it was Huh?
It's not a fire.
It's not a fire drill. A fire drill will be a lot louder.
And it also be a beep. It's a fire alarm. It's not the fire alarm. This is not what the fire alarm sounds.
No, it would be going.
My sister just messaged me and said fire alarm, and she works in the main office.
All right, then never mind.
It is a fire?
I mean, I don't think it's a fire, but she said fire alarm.
Oh. Okay. Let me pause this thing on. Yeah, David didn't come back yet.
Oh, sorry.
Okay, so to use this analysis technique we're doing, the sample mean, pardon me?
Did you unpause the recording?
Yes, thank you. So the distribution of the sample means turns out to be normal if the number of data points is greater than 30 or if the population is normal. So in our case, my population was normal, and so I could use it for any value of n. If it's less than 30 and the population is not normal, then you'd have to use some other technique. So here's the procedure that we're going to follow. I'm going to demonstrate it, and then we'll go back and try to figure out what the heck they're talking about. So first thing you do is you calculate the sample mean. A lot of times in problems they give you that number. And for our assignment that I'm not going to assign yet, I'll assign it next time, you're going to actually calculate the sample mean from a list of data. Then you calculate the sample standard deviation, which again in Excel is easy. Just use the built-in function. You estimate the standard deviation of the sample mean. So if we go back to my example here, wherever it is, it's the standard deviation of this information, not of the original data, but of the means of the data for the various samples that can result from that population. And it turns out that you can estimate that by taking the sample standard deviation and dividing by the square root of the number of samples. So the sample standard deviation is pretty close to the population standard deviation, but as you increase the number of samples, the standard deviation of the sample means gets smaller. So let me just show you that from my, whoops, wrong button. So if I go back to my original data, the standard deviation of the population is about 3. And if I look at the standard deviations of all these different samples that I generated, you've got 3, 4, 2, 2, 3. You know, they're all around 3. Some are bigger than 3, some are less than 3. So this is the standard deviation of the sample, which is pretty close to the standard deviation of the population. But the standard deviation of the means is going to always get smaller the more data points that you test, because you divide by the square root of it. I could demonstrate that with Excel, but just believe me in this case. Okay, then what you do is you find what are called critical t-values. A t-value is like a z-score, but it takes into account the fact that the fewer data points you have, the more uncertainty is in the calculation, and therefore you have to take a wider spread. The interval has to become bigger to maintain the same level of confidence that you are including this population mean within those two numbers. And it turns out the critical t-value you can get from a table, and what you need to know is what confidence level you want to use and the number of data points. They call these things called degrees of freedom, but it's always the number of data points minus 1. So if you have 20 data points, 19, you have 19 degrees of freedom. If you have 30 data points, you have 29 degrees of freedom. And then finally, you can calculate, well, we want to calculate this interval where we think the population mean is going to be. And we take the sample mean and we subtract what we call the margin of error, and we add the margin of error, this same number that we add plus or minus. And the margin of error is using all the stuff we've calculated in previous steps. You take the critical number that we get from the table, you multiply by the standard deviation of the sample means, which is S over the square root of n. So once you have E, you just add and subtract that from the mean, which you've calculated in the problem. So let's go through, we'll start on one example. We'll look at these steps. So here's the example, and what you'll have as far as an assignment is I won't give you the mean and the standard deviation. You'll need to calculate the mean and standard deviation, but besides that, the procedure is exactly the same. So what I have is I've taken 20 measurements from a population. The mean is 52, and the sample standard, so this is my sample mean. It's the average of these 20 measurements. The sample standard deviation is 2.6. So I've applied STDEV to these 20 data points, and I've come up with 2.6. The question is, what is the 90% confidence interval for the population mean? So this is a sample mean. Where's the 90%? It's going to be 52 plus or minus some number. We've already done steps 1 and 2 because we already have the mean and the standard deviation. So we skip. So we have the number of samples, 20. Degrees of freedom is 19. The standard deviation of the sample means is the sample standard deviation divided by the square root of the number of data points. So that's 0.58. So that was step number, what step was that? Go back here. Estimate standard deviation of sample means. Okay, that was step 3. The next thing is to find this critical t-score, and you'll see that this number is pretty close to what we did earlier. You remember when I did this previous problem, like from chapter 5, I used 1.96 multiplied by the standard deviation of the population. So it's going to be a number close to that, but not exactly. And since we don't have this in the book, we're going to just look it up online. So I'm going to show you how to do that, and I'll show you in the video. I've already made the video for the homework assignment. But you go to Google and you'll search for critical t-value table. And the first choice is that. So we're going to use this table. And you can see it has this distribution. This is what's called a t-distribution, not the z-distribution, but it's t-distribution. And in this table, you have the left-hand column is the number of degrees of freedom, which we said were 19, 20 minus 1. And then at the bottom of the table, you've got confidence intervals. So each confidence interval has a critical t-score associated with each degree of freedom. So we take 19 degrees of freedom, go over horizontally here. We're in the 90% confidence column. and we get 1.729. So that's the number we're looking for. So T critical is 1.729. So all we have to do to find the margin of error, we just take this critical T-score we got from the table, which was a function of the number of degrees of freedom, which is the number of data points minus 1, and the confidence interval, so that's easy to figure out. You multiply that by the standard deviation of the sample means. These two numbers multiplied together give you 1, the number 1. And then your confidence interval is going to be this minus that and this plus that. So the confidence interval for the population mean is 50 minus 1 and 52 minus 1 and 52 plus 1, which is 51 and 53. So our 90% confidence interval for the population mean is between 51 and 53. Now what that really means is that if I use this procedure with a set of sample data, 90% of the time it's going to correctly have the population mean in the interval that I predict. 10% of the time it's not. So, that may be, so there are different confidence intervals depending upon how close you want to be or how confident you want to be that the numbers that you specify on either side straddle the actual population mean. So next time we'll look into this a little more detail, and I will give you the assignment for this, finding the confidence interval.